on that Friday mindset already? Okay, so you're saying a cation has more protons than electrons. How did that come to be? How does that even happen? You can tell me, how would an atom acquire more protons than electrons? Nope. I want to know basically the most simplest answer you can give me that would tell me how it came to this place. Jillian? You. Losing or gaining electron, right? So
You can't lose or gain proton.
correct. So that's kind of falling into my next couple of questions. So I was hoping that maybe we got that far, because then you're kind of picking up what I'm putting down. But we have a loss of electrons. That's how it became a cation. Because you can't gain protons, so you can't be like, hey, let me just add a little proton or a plus charge here. I'm going to be simply losing an electron, and that's how it become overall positive, because there's no longer a balance between electrons and protons. All right, so I think we can all maybe put things together now. Kim, what do you think for an anion? First off, tell me which is greater. And how does that come to be? Right, that's due to a gain of electrons. Now, Darcy, you were right. This can happen in a chemical reaction, because during that time there can be an exchange of electrons. But I just wanted to know like the basics part. Okay, chemical reactions are a couple of units away from us. All right, so consensus here to what will always stay the same. Protons, right? Because that's going to be our rock, right? Our proton's going to be our identity. So if I say I didn't show you guys this yesterday. My absolute favorite element is element number 83. What is it? Don't have to memorize it. Look in the periodic table. 83. Bismuth. Who's ever taken Pepto-Bismol? All right, we've all had upset stomach or thinking of the commercial. Okay, so bismuth. This is from Dr. Rabinovich at UNC Charlotte. So I worked for him and another professor last summer, and working at UNC Charlotte in the summer for a grant pays really good. So if you ever want to get involved with science, volunteer your time. They can also hire you, contract you. They contracted me to make 3 organic chemistry labs for teachers and develop apps and websites and teacher workshops and all this stuff for $10,000. Pretty good, right? So get your lives into science someplace. But he asked me what my favorite element was, and I said bismuth. And then the next day I had this on my desk. Okay? So I'm passing around. Baby it. It's a little fragile. But this takes on different colors that you're going to see because of a different charge. There are actually quite a few charges that bismuth can take on. +1, +2, +3, and I'm just going to put ... because I can't remember the exact number they can take on. But that's why there's different colors, because different colors of bismuth, different charges of bismuth have a different color associated with them. So you can kind of see it in ooh and ah as you go. But what will always stay the same is bismuth's protons. How many protons does bismuth have? 83, because that's its atomic number. Great. Okay. Now, I can have different isotopes of bismuth, and that's going to have a different number of what? Neutrons, right? Different isotopes. So I'm scooching down this question that nobody's even seen yet. What particle changes to create a different isotope? You guys just said what? Neutrons. And as the neutrons change, what actually is changing about that atom? The mass number, or the atomic mass. I'm going to say mass number because it's a little bit more specific. Okay, so isotope, you should be associating with neutrons changing. Ion, you should be associating with what changing? Electrons changing. What should you be associating with protons changing? Nothing except for the element changing, right? The actual identity of the element. All right, so I feel like we got a decent grasp on that. Problem set 4, I want to see on your desk that you've started it. You can do that in 3 questions done. That is totally fine. But if you don't start it, you're never going to start it. So problem set 4 is on your desk. Second, let me go over a question on reading guide 5 that I already know everybody has. Number 9. That's how it would grow in the ground. if you wanted to isolate bismuth from tetrabismol, one of my AT students calculated one time, saying, I'm going to do this. It would take like 900 bottles to get a substantial amount. And I was like, I am not buying 900 bottles of tetrabismol. I've already had to like buy, what we had to buy? Oh, we had to buy like 9 bottles of olive oil one time for the chemical experiment. And all these people were like, why the hell is olive oil? I look weird in Walmart. So, anyway, yeah.
Those little poppers that you throw on the ground.
Yeah.
Let's take like 5,000 of them, and they will get silver out of them. Those are just tiny bits of it. We spent like
Silver,
$100.
silver's gotta be like an impurity or something in there because
Yeah.
I think it's iron and magnesium or something that actually is in the poppers. Because those are much more prevalent than silver. Okay, so you guys keep passing that around. Here's my answer for you for number 9. So I already know this is the question. So the question for number 9 said, why will yellow light produce a photoelectric effect on potassium, but red and orange light will not? Whose theory does the photoelectric effect support? So here's my little picture, and if you can see this, then give me a thumbs up. Can you see the yellow light here? It's really hard to see there. Okay. So basically, this little gray piece right here, this is a piece of potassium metal, so K metal, potassium metal. Metals all have, all elements have tons of electrons, but metals specifically, they couldn't really care much more for their electrons. They're fine to give them up all the time. That's why we use copper in electrical wiring, because it's free. It's like, yeah, sure, send my electrons down the line, and I'll continue to conduct them, and that's how we get electricity. Fun fact, the mass of all the electrons that make up the internet is the mass of a strawberry. Your precious internet is a strawberry. Okay? Isn't that crazy? Those stats are from like 2 years ago, maybe it has grown. But like literally, the internet's just a bunch of electrons sending information. Now there's light and stuff involved too, but that's still even electrons. So speaking of light, we have the photoelectric effect. Photo stands for, like photosynthesis stands for light. Guess what electric kind of refers to? Electrons. And then so it's basically the effect of light on electrons. That's all it is. So as we have these 3 different forms of light, we have red light, we have orange light, and we have yellow light. You can see it actually drawn the red light with a long wavelength. It's got a long separated kind of wavy pattern. The orange is a little shorter, and then the yellow is like really fast. It's fast, it's got short wavelengths, and it actually has the most energy. And we'll really get into the details of this today, but the most energy from that yellow light is able to send that energy to the electron in the potassium metal and pop it out. Think of, you're walking by the grocery store, you have the shopping cart, and you take your hands off. What happens? Sometimes. Well, I'm thinking about something that would relate to something popping out, and maybe you feel that. You're shuffling around your shock seal. Shock. There's a little shock, right? So static electricity. So sometimes now that's related to friction and a little bit more, but it's basically the same thing. You have enough energy, it hits the electron, it pops the electron out. This red and this yellow, they don't have enough energy. They're just going to be absorbed, and then there's not enough energy to pop the electron out. So it doesn't have a very significant photoelectric effect. We actually take advantage of this by using these. Hold on, I need one light to stay in the dark. Alright, so these guys, these lovely calculators, they require the photoelectric effect because this little screen up here has the ability to absorb photons, which is coming from our light out here, just the fluorescence in the room, and that's how they charge. If I left these in the dark the entire time, they would not work. You'll notice there is no battery on these. Can't steal these batteries, guys. Okay, so these are going to be charged by light. That's how a lot of other electric systems work. They need the light to allow for energy to be transferred. So basically what I'm telling you is this right here. Light photons, which is just how we call a packet of light, they can help electrons be emitted or transferred or flow, and that helps us give a current. That helps us get a current to flow, which powers our devices, at least the ones that are kind of like solar powered. Question?
Oh, I was going to say, I know phones, they're trying to make it so we charge off of like
Solar?
light.
Mm-hmm.
Yeah.
So you basically have to have a solar charger that absorbs energy, and they can transfer most of them can. Obviously solar, that's what it's meant to do, is take in light and transfer it into electrons. and you just plug it up into your phone. It's really, like, I know there's actually some out there, but one of the guys I work with at UNC Charlotte has one. He just sets in his window. Great. Another question here. Reading guide 5. Yeah.
Does it still have more energy because the wavelengths are higher?
Yes, that's the only reason it has more energy, because the wavelengths are shorter. So the wavelengths are tighter, means it's shorter, means they travel faster. Faster moving means more energy, yeah. That is the nature of that color of wavelength. Red, and I'll show you the whole entire electromagnetic spectrum. Red light is on the infrared side of things, and infrared is how a laser works, kind of. A laser works. And also this guy, like, this guy who talks to the projector, it works by infrared signals. You can't see that there. And then purple light, which is on the violet side of things, is closer to ultraviolet, which is UV, which also you can't see. But we all know UV is not great for you, right? UV is going to cause some skin damage and mutate your DNA. It's because it's so tiny, it can squeeze through your cells and affect them. Yeah.
Higher frequencies of the visible light spectrum besides yellow have an effect on potassium as well.
So yes, higher. So what she asked is, we only consider these 3 colors, but there of course are more. So if I have green, it's even faster than yellow. So it's got an even smaller wavelengths, which means higher frequency, like Jillian's saying. It's definitely going to pop out an electron. What's on the other side? Green. Blue, and then, so this is good. I'm trying to draw them smaller. There's some hair on this part. So that's going to definitely pop out electrons. And then what else? Purple. Violet. Oop, that's not violet. That's green. Now, I hope that we don't have any colorblind people in here. I usually have at least 2 a year. Except for Justin. So you're going to have a little hard time with this unit. You have a good friend who won't lie to you. Dude, this is green. It's like purple, okay? So, more questions on reading guide 5 right now. Okay, hold reading guide 5 at your desk. Yes, ma'am.
What was
The law or theory is the photoelectric effect, which is de Broglie's equation. De Broglie. The photoelectric effect. Oh, sorry, no. De Broglie's equation. De Broglie's theory is the particle-wave duality. Particle-wave duality. And I think that really is self-explanatory. It's got a duality. Think of like Two-Face or some Two-Face and like Batman. Yeah, okay. It's got two sides that you need to consider. The particle nature of it is that light can affect particles. The subatomic particle is called the electron. The other part of it is that it's a wave, so it does have a wavelength and a frequency and energy associated with it. So you got to consider both sides of this forefront. So thank you for asking that, because I didn't mention that. All right, so reading guide 5. Anything else right now? All right, hold down on your desk for me. And we are going to now go back and do the lab we didn't do yesterday, which is called the Beanium lab. I'm going to give you guys about 25 minutes. You have this paper already. I gave it to you yesterday. It's on the back of your isotope notes. On the back of your isotope notes. I have also been kind enough to try to copy this for you for time's sake and for clarity's sake, and what's going on. So, on your lab, give me a thumbs up if everybody knows what a lima bean, a kidney bean, a pinto bean, and a black eyed peas looks like. Hopefully somebody at your table knows what that looks like. And I'm going to leave it to you guys to read the instructions, fill out your table, and we'll come back together in about 25 minutes, okay? Yeah. Leave it on your desk, we'll get to that shortly. All right, does everybody have this? This is a fine, no safety hazard unless you eat the beans lab. So you're fine with no goggles and open toes, okay? Go to your pain lab patients. Get your notebook out. All hands on deck, because you won't finish in 25 minutes. Gotcha. Thanks. What we did yesterday is we did a couple of exercises to link online. So under last night's homework.
Yeah, I went on your website.
Perfect. All right. So you saw Chloe. What's up? I do. I'll get you one in just a second, okay? So if you look under last night's homework, Thursday, warm-up activities, we did that for quite a bit. So I would definitely go back to that. Simulations are on my website. They're on the links page, which I'm not using. And then basically after that, we did. Okay. So your groups today will hopefully help you with this whole year too, in your kind of downtime. Okay, and I'll put the video outside. The video in the fourth period, I'm going to put it up in the first period.
Okay.
Okay?
Thank
Does that
you.
work?
Yeah.
Justin?
I'm just gonna clarify, so I don't do you don't do wait till next week to do that. I just do the chemical. Create.
So you need to so the other
Alright, I'll go ask you
like, you know, in the middle of me talking, you don't ask me. So I gotta help you. Thank you.
Do we really have to pour out the beans and sort everything?
Yes, you guys have to sort. That's why you got 3 or 4 people, right? Get everybody on it.
Hey, guys, I'm ready.
Alright guys, so there's a bag of beans at your desk, and you've got 6 to 8 hands on deck. Yes, you do have to mass out those, and you need to separate the beans. You're not going to do it.
You know what? This is why. You can't have nice things. Wait, never mind. You realize it's all part of it? I didn't do it. Dude, if you've been like a day here, it's like a week. Okay, guys. I know you all want to do as much as I do. Robbie, wait, and you were in elementary school, did you like grow one?
I did.
Robbie, Maddie did.
I had the best one.
Yeah, for like 2 years.
Know how because I think you do.
I was in the stands for third and fourth grade.
Okay, so I and then I'm also came back and then I'm
Oh, yeah. In North Korea, so they can tell you they're fine and dandy. They have these big stoves set up at the border. And you can tell which ones are ready because they don't have smoke coming out of the chimneys. So they're like really set. I do like this.
So I'm sure you guys have moved past this part, but can you see these numbers okay? With the photon energy, it says blah, blah, blah times 10 to the negative 21st. And then second, wavelength range, I think you can see that one fine. And the last one has 3.00 times 10 to the 8th meters per second. And if you need to write that down, that's more for yourself. I'm going to scroll down to the Model 2 for the emission spectrum, and that's going to be a little harder to see on your paper. So I blew it up here so you could see a bit better. And I'll read these off to you if you need me to. For a hydrogen, where it says, list this is question 8. List the spectral lines for the hydrogen gas by color and corresponding wavelength. So question 8, I'm just going to read these off. You can't see these. 410. What is the unit for that 410 right there? Nanometers. You see wavelength in nanometers. Nanometers, right? We got that metric stuff coming back to us. 434, 486, and 656. And you can see the colors violet, blue-green, and red. So I'm going to let you guys look at that, and then you can kind of move a little further. What question are we on? 11. I heard 11 was my greatest, I think. Okay, so you guys keep moving. And notice the back, and you'll notice that if you are able to move on, homework sheet is what you're working on. If you don't finish it, you'll finish your homework. But try your best to get through a little bit of this. We're going to start talking about this more in depth in about 5 minutes. All right, guys, look back up here. I've got the worksheet right here in front of us. You have this on your desk, so let's walk through a couple of these together to make sure we're on the right track. We've discovered some of the same things, and I want to hear your conclusions on this. So I might go a little further than you guys got, and that should be okay because you should be writing them down as we go. I'm gonna have to work from the computer, guys, because that side of the smartboard is real crazy. All right, so you should see that you've got this white light. Who's ever seen the Pink Floyd T-shirt? Right? You see the light is separated through a spectrum. We are going to have our own spectrums, and we're going to hold them up to the lights next week. We're going to hold them up to emission spectrum next week as well. I'll have a video to help you see what this actually looks like, but this is just a white light. These are all the colors, their energies, but what do you notice about their speeds? They all travel at the same speed. Okay, so that's one of the discoveries you're making. Second, do all the colors of light have the same energy? No, but do they all have the same speed? Yes, so energy and speed are two different things. Speed is how fast you're traveling per time, right? The distance you're traveling per time. Whereas energy is just like the inherent joules that are present within your particle. So those are two different things. Sometimes those get confused. Which color has the highest energy? Violet. Oh no, we can't say purple, right? We got to say violet because we're talking about it being closer to the ultraviolet side of the electromagnetic spectrum. Oh, while I'm there, there's a blue laminated sheet on a couple people's desks. Can you guys pass to make sure everybody gets a blue laminated sheet? Because I want you guys to see the electromagnetic spectrum. I'm going to bounce back and forth between the worksheet and some notes, so bear with me. I like to keep it interesting. But this is the electromagnetic spectrum. Find it on your laminated blue sheet. It's going to be on the back where it has the Bohr model. Not on the periodic table side, on the back where the Bohr model is. Make sure you guys have them. There's bunches of them around the room, so just make sure you get one. So mine looks a little different than yours, but we are special. We have the ability to see visible light. Not every organism in the world can see visible light. Butterflies, for example, see in UV. Ultraviolet light. They detect ultraviolet wavelengths. They cannot really detect visible light to the extent that we can. They might see some violet, but that's about it. So different flowers have different ways that they emit energy. Some flowers specifically will emit UV, and that attracts butterflies. So not everything can see the way we do. We can only see in the visible light spectrum. But we know there's other forms of energy. We take advantage, or sometimes we take advantage because we want a little darker tone, right? You want to get tan. You can't see UV, but you can feel it. You actually feel it a lot when when you have too much, because then you have a sunburn, correct? Okay? Who's ever had an X-ray? Now, we don't see the X-ray, we don't feel the X-ray, but we have this great machine that can detect the X-rays and bounce the light or the energy back to show us like if we have a broken bone or not. Gamma rays? Who's ever seen a gamma ray? Who has seen the effect of a gamma ray? The Hulk, right? Okay, so we know that they exist. They're very, 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 very high energy. They mutate your cells to the extent where you could become the Hulk if you were that cool, or you die of cancer. Okay, so there's two options in between. But gamma rays will damage your DNA, like extremely. UV does a little bit. X-rays do a little bit. That's why when you go to the dentist, sometimes do you guys wear a vest? Yeah. Okay, so you're blocking that lead vest is blocking the X-rays from penetrating through to your body, so they can only get your teeth, because you shouldn't have too much X-ray exposure over in like a specific amount of time, because then you could have damage. That's why people who work in like nuclear power plants or MRI machines or have X-rays or work with X-rays a lot, they wear like a little meter. Have you ever seen that? And it measures the amount of radiation they get, and if they go over, they literally can't work for like, until their cycle is up. So they have to protect those people. So on the other side of things, we have infrared. Where did I say we had infrared earlier? Lasers and the detector that says TV turn on, right? That's infrared. And I might be able to show you if I can turn this on. I can shine this at that, and then you can actually see the infrared. Okay, so I'll try that in a minute. Radar, sonar, radar. There's different forms of that. We don't really see that either. Who's ever heard of FM and AM radio? Okay, if you listen to AM radio, you're weird. If you listen to FM radio, it's okay. No, I don't judge you. But these have really long wavelengths. So how tall are you guys in meters? Okay, a meter is about a yard. About. So how big is a yard? 3 feet. Okay. So who's 6 feet tall? Okay, who's close to 6 feet tall? Okay, so you're about how many meters tall? You're about 2 meters tall. Most of us are a little less than 2 meters tall. Look how many meters an AM radio wavelength is. 10 to the 4th. How big is that? Okay, give me the number. Expand that. 1, 0, 0, 0, 0. So what is that? 10,000 meters. That's how long an AM radio wavelength is, but we can still detect it. We can still hear it because the radio catches our radio in our cars, or, for example, capture that and put it out as sound waves for us, because that we can't see it or hear it otherwise. FM, okay, they're 1 meter. They're a little shorter than us. Okay, that's kind of cool. But gamma rays, so I'm assuming it's fine. Okay, gamma rays. I'm not going to do that many zeros. Okay, but there's 14 zeros there. Really, 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 really tiny, and that's why they can squeeze between your cells, even between your DNA, and start to do some damage. Yeah.
Where do microwaves like?
Microwaves. Did I skip that? Oh, it's in here. I will tell you. I'm gonna X your voice in my radio. Okay. So I have to memorize this in AP. I made up this really silly way. Gonna X your voice in my radio. Gamma, X-ray, UV, visible, infrared, microwaves, radio. Because all of these basically are radio. Okay, they're right in front of radio. But that screen on the front of the microwave, have you guys ever seen that you can see your food, there's like little dots blocking your way. The microwave is just a hair too big in that little teeny hole. Because if the hole is too big, the microwave can escape and damage you. So they make that little hole so you can see your food, but not too big for the microwave to escape, because the wavelength literally gets blocked because it can't get through that hole. Isn't that cool? But it also does affect your food. It literally just excites the water molecules, makes them speed up. When they speed up, they get hot. Boom, you got hot food. Or really crusty food if you leave them too long. Okay, so this is the electromagnetic spectrum. You will always get this from me. You will always get the Bohr model and the electromagnetic spectrum together so that you can understand how they relate to each other. So, while we're doing that, let's go back here. Let's talk about the variables we're going to be speaking of. I have about 10 minutes left, so I'm going to work through probably one problem. But you guys have this on your notes sheet from the historical model on the back. Pull that up for me. I've given you a lot of stuff already for the unit. You just got to keep up with it. But I like to give you the works. It's on the back of the historical model. So you can get some historical models on Monday. On the back of it, you have the modern atomic model. We're talking about the modern atomic model, which is past Rutherford, past JJ, past Chadwick, past Millikan. We're now getting towards Bohr and Schrodinger. All right, so here we go. You have this in front of you. Yes? Yes. See. Okay. So we have seen maybe a wave before. I even drew them on the board here, but you couldn't really tell. There's a crest. There's a specific wavelength in between each crest. But if you had to define a wavelength, it's literally the length between two crests on a wave. And so the wave does continue on both sides, and the wavelength itself is different for every color of light. Every, even from X-rays to gamma rays, that wavelength is different. So the wavelength symbol from crest to crest, from here to here, it's a lambda. It's like an upside down broom or a Y. It's called lambda. So that's down here. It's called lambda. And it's like this little funky upside down Y shape. So make sure you're labeling that for yourself. You should know what a wavelength is represented by. Second, the speed of this wave does vary. And so the speed, we actually have another name for it. It's called frequency. Did you see that in your reading guide last night? Okay, frequency is labeled with the variable. It looks like a V right here, but I'm going to draw it bigger for you. It's actually like a V with a little tail on it, like that. Fancy V. Okay, that right there represents frequency or speed of the wave. So the way the relationship you should make is that long waves have a slow speed. Write that down. Long waves have a slow speed. So I'm going to say long wavelength equals slow frequency. Right, that's a V. Okay? Second, you should be able to tell me then, what would be the speed of a short wavelength? Be really, really fast. It runs across because it doesn't have much to travel to make its next hump of the crest. So long wavelength has a slow speed, so vice versa. A short wavelength is fast. It has a fast speed. So as you guys are writing down some of the definitions, I'm going to leave them right here for you. The amplitude is my least important definition. Wavelength, the distance between two similar points on a wave, that's important to know. And we label it lambda. Frequency is how fast it's moving, but it's always, like if you're looking at one point, how many times a wave comes past you at that point. It does relate to its speed. But it's number of waves that pass during a specific time, and we can either measure that in waves per second, which we don't always write for the waves part. We always usually just write per second, so that's like 1 per second, as you can see here. Per second, meaning it's on the denominator, can additionally be written as second to the -1 power, or the guy who discovered this, guess what his name was? Hertz. HZ, Hertz. So HZ is the abbreviation, because if you're a scientist, your goal in life is to name something after yourself. There will be an enlonium up there some point in time, or I will come up with a law or something, right? But I will do it in your lifetime. But in this respect, we do have to recognize there are many ways to represent frequency. That's really the point of this, all this nonsense right here. So give me a thumbs up if you got that part down. Okay, just kind of seeing where we are.
Teachers, please turn on your announcements at this time.
I got 5 more minutes, but hold on. Let me finish this part here with you guys. So the relationship between wavelength and frequency. There is a relationship. And the way, since we're talking about light, we're talking about energy, we're going to relate them to energy and light separately. But the equation is C is equal to lambda times frequency. Or what's lambda again? Wavelength times frequency. There's your multiplication. C represents the speed of light. Okay, so speed of light is equal to wavelength times frequency. Let's figure out what units we should be using to actually represent this appropriately. So if I'm talking about length, what unit comes to mind? Meters. Okay, generally the wavelength will be in meters or in nanometers, but we cannot use nanometers in this equation at all. That's where you have to convert from nanometers to meters, like we did with dimensional analysis, showing your units and canceling. So that's going to come back to us. Frequency. Again, what was that unit that we had up there? Okay, so we had hertz. What was another version of that? Okay, so 1 over seconds, or seconds to -1, right? Okay, so if I have meters, or nanometers, remember you got to convert to meters. Meters is over 1, because that's a numerator. And hertz, or wavelength, or frequency, is 1 over seconds, right? What will the units of the speed of light be? Meters per second, because nothing cancels. Meters per second. They both have to stay together collectively. So this is how your units will always work out. Wavelength should be in meters. Frequency should be in per seconds. Speed of light should be in meters per second. Okay, I'm going to stop it there. We did not get as far here. So you guys will finish the total worksheet or EMS. You will probably, you need to finish, or not finish, you need to continue concept work. You should be capable of most of it at this point in time, but I will not take it up on Monday. So I want you to kind of keep looking at the isotopes, because those are the hard ones to get sometimes. You have your notes in the back. I want you to hold on to that until we're done with the isotopes for now. Okay?
About one